All right, let's get started for the day. Okay, so today we're going to be talking about cyclohexane, and we're going to be going over all three types of strain that we've covered so far and trying to understand how that strain is manifested in the different conformations of cyclohexane. Last night I sent an email, told you to make a model, and if you have a chance, take a look at the conformational handout on Moodle. We had a chance to look at the conformational handout on Moodle. Several of you. Okay, that's good. If you didn't, bring it up now. So it's going to be the first handout up on Moodle. It's going to be important to see. Right, so when you bring up that handout, just scroll down to the page Conformational Energy of Cyclohexane. Right, and that's what we're going to look at today. Okay, so when we ended class on Wednesday, we were talking about different ring systems and the ring strain inherent in those ring systems if they're completely planar, right, and how they can kind of adopt different conformations in order to balance out the different types of strain in those systems, right? So we were looking primarily at balancing of ring strain with torsional strain, right? We said that when these systems, cyclobutane and cyclopentane, when those carbons in those rings are completely planar, then torsional strain is going to be at a maximum, right? And so to relieve some of that torsional strain, they're going to bend out of plane, right? Adopt a slightly non-planar conformation, right? In which case we're slightly increasing the bond angle strain, right? But at the same time we're relieving more torsional strain, so it's allowed. Okay. Those systems aren't that interesting. I mean, it's good to know that they can bend out of plane, that they're not planar, right? But if we do the same analysis with cyclohexane, right? If we assume that cyclohexane, all 6 carbons are in one plane, what would the internal bond angles have to be of that 6-membered ring? Do you know? What's that? 120 degrees, right? Which is, larger than ideal. So the ideal bond angle is 109, right? If all 6 carbons were in one plane, the internal bond angles would have to be 120, right? If you take your model and try to get all 6 carbons in one plane, hopefully you can see your model's doing what my model's doing. It doesn't really want to be in that conformation, right? It doesn't want to be completely flat, right? So what happens if you take a look at that page of the handout, you can see that cyclohexane can adopt a number of different conformers. Okay, with the lowest conformers, lowest energy conformers being the chair conformer. Okay, in the chair conformer, we're going to be able to adopt almost ideal bond angles around each carbon. All right, so in planar form, you could feel how much stress and strain is in that system. Right, and once you get this into a chair conformer, hopefully you can feel that the molecule is a lot more comfortable. Right, so for the chair, just so everybody's on the same page, for the chair, right, what you want to do is you basically want to take, hold the 6-membered ring by 2 corners, right? Take one corner and pull it up, take the other corner and push it down. Okay, that should be the chair. Good. Okay, when this molecule is in the chair conformer, what is torsional strain? What is the level of torsional strain in this system? or how can we assess torsional strain? Right?
It wouldn't be at its lowest, but it would be somewhere in the middle. When you look down one of the carbon bonds.
Good, so we look down any one of the carbon-carbon bonds in that six-membered ring, right? And when you look down any one of the carbon-carbon bonds in that six-membered ring, what do you see? What relationship do you see? Staggered, is it eclipsed, somewhere in between? Yeah.
All of them are staggered?
Good, all of them are perfectly staggered, all right? And so in chair form, torsional strain in this six-membered ring is going to be minimized, right? We don't see any, well, it's not that we don't see any torsional strain, but it is at a minimum, because all of the bonds are going to have a completely staggered relationship, right? Any bond in that six-membered ring that you look down is going to be completely staggered. All right, so we have a minimum amount of bond angle strain in the chair system, and we have a minimum amount of torsional strain in the chair system, right? And so when you look at the energy diagram, right, for the energy of the different conformations of cyclohexane, you can see that there, the lowest energy states are going to be two chair conformers. All right, everybody can see that? Handout? Yep. Okay. So you can see as this molecule undergoes conformational change, right, at one end of the energy spectrum, there's one chair. At the other end of the energy spectrum, there's another chair. All right? This is not the same chair. This is not the same conformation. Okay, so let me orient you a little bit. So this is a drawing of chair cyclohexane. I'm going to teach you how to draw these and understand them. Right, but basically this drawing, we're looking at the chair cyclohexane from the side. Right, so this corner here, right, this is going to be the front of the ring. This corner back here, this is going to be the back of the ring. Right, so see if you could hold your model up in front of you, right, to get it into kind of an orientation where you're looking at it like a chair. Right, so the corner in front of you should be pointed up, right? The corner in the rear should be pointed back, right? You're kind of pointing one of the corners at you, directly at you, and then just rotating it, I don't know, maybe 10, 20 degrees to the side, right? Is anybody not able to see that perspective? If you are, that's okay. Everybody's able to translate from a three-dimensional model to this drawing up here? Okay. Now, when this molecule is in a chair, we can divide the groups around this molecule, or in this case, the hydrogens around this ring, into two different groups, right? And on my model, I have them colored. Okay, so you can see there are bonds that are either going straight up, right? I have 3 bonds that are going straight up on top of the molecule. Draw a chair here. Okay, so my gray bonds here are going straight up. When I draw them off of that ring, I'm going to draw them going straight up. Right? And then I have 3 more on the bottom, right? Same color, that are going straight down. Okay, and on the drawing, I would draw those going straight down. Does anybody know how we refer to these hydrogens? Straight down?
The ones that are going straight up and straight down are the axial, and then the ones going around, the equatorial.
Good. So the ones that are in black that I've drawn here, we refer to those as the axial substituents, in this case the axial hydrogens. Right, so just put an A next to each of those. Right, and then you can see on my model in green, right, I have 6 hydrogens that are going kind of out of the center, right? So there's one here, 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 and here, right? They're maybe slanted slightly upward or slightly downward, but they're all radiating from the center, right? We refer to those as equatorial hydrogens. Okay, so you can see that there are 6 in one conformation, right? There are going to be 6 axial hydrogens and 6 equatorial hydrogens. All right, on my model, again, you can see that the axial hydrogens are gray, right? And the equatorial hydrogens are green. And when this molecule undergoes what we call a chair flip, right? We go from one chair to the other. To flip this on the model, what we're doing is we're taking the corner that's pointed down, we're pulling it up. We're taking the corner that's pointed up, and we're pulling it down. Okay, when I do that, what happens to the axial substituents? They become equatorial. What happens to the equatorial substituents? Become axial, right? So everything that was axial, right? So you can see here, everything that's axial is green, everything that's equatorial is gray. When I do the chair flip, right, pull one corner down, push the other corner up, right? Now everything that is axial is gray, right? Everything that's equatorial is green. So the substituents in one chair that are axial, right, when you do the chair flip, they become the equatorial substituents. They have to. There's no option. Right, questions about this? No. Okay, drying chairs is going to be relatively easy. First of all, if you drink Budweiser, you can recognize this as the Budweiser symbol, right? So you can use that as inspiration if you want. Otherwise, there are rules to follow to draw chairs. Right, so the sides of the chairs are always going to be slanted. Okay, so what I do when I draw chairs, I'm always going to start, I mean, just kind of have it now, but start on the left side. All right, but the sides, they're slanted, but they also are going to be parallel with one another. All right, so those are the sides of my chair. Okay, then I'm going to draw 2 more parallel lines. All right, and then I'm going to finish this off with 2 more parallel lines. All right, so all this is really a series of parallel lines. All right, so I have those as the same. Those are the same. Right, and then those are the same. Okay, when we draw the axial substituents are going to be really, really easy to draw. All right, so all right, so axial substituents, when we draw them, there's going to be an axial substituent on every carbon. Right, and we're just going to draw a straight line coming off that carbon, right? The direction that we draw the line depends upon which way that carbon is pointing. So if the bonds leading to that carbon are pointing up, right, we're going to draw that straight line going up. Okay, if the bonds leading to that carbon are going down, right? We're gonna draw that straight line going down. All right, so one here, one here. Right, so I just present these all as hydrogen. All right, so axial substituents really, really easy to draw. Right, you just follow whichever way the carbon is pointing, right, and draw a line going straight up or straight down from that carbon. Questions about this? Okay, one thing to note, right, you can see here for the hydrogen coming off this carbon in the front, when I drew it straight up, I tried to show that it's overlapping this carbon-carbon bond in the back. Right, so I just erased a little bit of that carbon-carbon bond in the back. Likewise, this hydrogen is coming off a carbon in the back, right? So the bond going to that hydrogen, I'm going to erase a little bit of that bond to show that this carbon-carbon bond in front is overlapping that carbon-hydrogen bond. Right? What I often see, or a mistake that I often see students make, is they start drawing me MC Escher drawings, right, of these impossible molecules where we have a bond in the front being overlapped by a bond in the back, which doesn't really make sense. Right, so just make sure that your perspective is correct and you're just not randomly overlapping bonds. Questions about that? Everybody gets that?
If you did a chair flip, would that drawing look the same always? Because it would always just change.
It won't, yeah, and we'll go over that. I'll show you how to represent what the chair flip. Okay, so axial bonds, the easiest ones to draw. The equatorial bonds are always a little bit confusing. All right, what you need to know is that an equatorial bond to a hydrogen or whatever substituent, it's always going to follow a bond within the ring. It's always going to be parallel to a bond within the ring. Right, so, for example, right, so you can see this bond in blue follows the ring bond that I've identified in blue. Right, same thing over here. Okay, so those equatorial bonds are going to be parallel to a bond within the ring that's 2 bonds away. Right, so this is the equatorial bond that we needed to draw, 1, 2. Right, the bond that we needed to draw, 1, 2. Right, so that second bond is always going to be parallel to the equatorial bond. Yeah, questions about that? Everybody sees that relationship? Yep. Okay, we go to the other corners, right? If we count, if we draw a bond off of here, we need to count 1, 2, or 1, 2, right? So it's got to be parallel to what I've marked in red. Right? And then the hardest ones are going to be these kind of funny ones in the middle, but they follow the same rules, right? So if we're drawing an equatorial bond off of this carbon, we just count 2 bonds in the ring, 1, 2, right? Or 1, 2. So you can see the bonds, the equatorial bonds coming off the middle carbons always have to be parallel to the ring bonds on the side. Okay, so draw these in purple, right? And they just need to be parallel to the bonds coming off, or the sides of the ring. Questions about representing chair?
Are you supposed to denote substituents as axial or equatorial?
No, that's just for today, just so you're oriented. Other questions? Okay. So what I want to do is go through this so we understand hopefully why this is going to be the lowest energy conformer, right? But I want to go through the whole energy spectrum on that's drawn out on the handout to understand the relative energies of the different conformers that are drawn there, analyzing for torsional strain, steric strain, and bond angle strain. All right. So in the chair conformer. Right? In this chair, all of the green substituents are axial, gray substituents are equatorial. Right? We learned that in the chair conformer, torsional strain is minimized. Steric strain is not something we have to worry about in the chair conformer. Right? And then bond angle strain is also minimized. Okay? To go from the chair, right, on that energy diagram, what's the next conformer?
Boat or half chair.
Half chair. And in terms of energy, where is that on the energy diagram? High, right? High in energy, right? So we're going from something that's really, really comfortable, right, to something that's really, really high in energy. So if you look at that half chair, to go from the boat to the half chair, all we're doing is taking one corner, right, one carbon, and basically bringing it up so it's in plane with 4 other carbons in the ring, right? So all we're doing, taking that one carbon and just shifting it up like that. Okay, when we do that, how does that affect torsional strain? Right?
It makes it maximize like along some of them except for the one that's up low.
Good, right? So it's not maximized for the whole molecule, but we can say now, can't keep this straight, there we go, right? Between these 2 carbons here, these 2 carbons here, right? There's going to be a maximum amount of torsional strain. We're increasing torsional strain here and here, okay? And then torsional strain is probably also going to be affected down the other bonds, right? So just by switching from this, right, moving a little bit up, we're really increasing the energy of the system because we're introducing much more torsional strain. Right? Questions about that? Yeah.
So the bottom 5, they're all supposed to be on like the same plane, correct? So
Yeah, when we go to the half chair, there should be 5 carbons all in one plane and then one kind of above or below. Other questions? Okay, after the half chair. So the half chair, that's the high energy conformer, right? The global high energy of this system. Okay, so this is going to be the highest energy conformer in this system. What's after the half chair?
Twist boat.
The twist boat. Good. So the boat is that's a conformer that a lot of people are familiar with when they study conformation. Okay, the boat, all we're doing is we're taking one corner, and we're flipping that one corner all the way up, right? So the 2 corners are both up. The twist boat, we can make a twist boat basically by taking those 2 corners and just kind of pushing them apart either one way or the other way. Okay, one way or the other way. You're in a twist boat? Yeah. Right, so this is the boat. So to twist the boat, right, we're just taking these 2 and bending them a little bit. Right? And if you look at the energy diagram, you can see that the boat is in a higher energy state than the twist boat. Okay, so why is the boat in a higher energy state than the twist boat?
Because twisting it makes the top part a little bit more staggered, right?
Okay, so you can see in the boat, right, we have a steric interaction, right, some steric strain. And that steric strain comes from the fact that these 2 electron clouds, right, going to these 2 hydrogens, they're trying to occupy the same space above that molecule, right? They're pointed right at each other. Again, it's not the atoms, it's not the hydrogens that are interacting, it's the electron clouds around those hydrogens. Right? This is called a flagpole interaction. This is a very specific steric interaction. right, only exists in 6-membered rings in the boat conformation, right? That's what is specifically a flagpole interaction. Okay, when we adopt a twist boat, what happens to that interaction? That steric interaction. Yeah.
I mean, it still exists, but it's not quite as bad.
Good, right? We're gonna minimize it or reduce it a little bit, right? So in the boat, those hydrogen atoms are pointed right at each other. The electron clouds are interacting, right? When we twist, now you can see they're not pointing directly right at each other. They're in the same, general proximity, right? But some of that strain is going to be relieved. Okay, so there is a steric interaction in the boat conformer that we can relieve by twisting one way or twisting the other way. Right, so that explains some of the energy reduction when we go from a boat to a twist boat. Right, what else is helping to reduce energy?
The base ones are not all in line with each other when you look down carbon.
Good, right? So if we turn the boat this way, right? So we're looking at the stern or the bow of the boat, I guess you could say, right? You can see if this is a perfect boat, the bonds down the sides, they're going to be eclipsing, right? So there's a maximum amount of torsional strain between the substituents on this carbon, right, with the substituents on those 2 carbons. If we twist, you can see some of that torsional strain is going to be relieved. It's not completely minimized, right, but it is going to be relieved when we go from a boat to a twist boat. Okay? So the 2 energies that are helping to relieve energy, or the 2 elements of strain that are being relieved whenever we go from a boat to a twist boat are going to be the steric interaction, the steric strain, right, between the flagpole hydrogens, and then torsional strain, right, with the substituents on the side. Okay, questions about that? No? Okay. And then finally, when we go down the other side, right, we're going to go back to a half chair and then back down to the other boat. Okay, questions? Okay, so the purpose of going over this is to show you that we can pick apart any system, right? We can understand the conformational of any system if we can break it down into the individual elements of strain, right? If we look at a system and say, okay, what is the torsional strain in the system? Separately analyze that system for steric strain, right? Separately analyze that system for bond angle strain, right? And then we can combine those and understand how comfortable is this molecule. Questions about that? No questions, all right. Okay, if you have a chance, just put a substituent, replace one of your hydrogens with some substituent, doesn't matter which one. All right, everybody has a substituent on their cyclohexane? All right, so put your model into a chair where that substituent is in the axial position, the axial orientation. All right, and try to put that model in front of you so it looks like a chair cyclohexane. Best you can, try to imagine it in 2 dimensions. All right, and then keeping that model kind of stabilized in that same position, I want you to do a chair flip. All right, so keeping it kind of in front of your eyes, all I want you to do is pull one side down and then push the other side up. All right, try not to change the perspective. Okay, when you do that, does it still look like a chair? Right? I don't want you to move the molecule at all. All I want you to do is put it in front of your face so it looks like a chair, right? And then do a chair flip. Don't move the molecule around, just do a chair flip. Does that chair perspective still hold? No, right? It shouldn't look like a chair anymore. Okay, and so that means when we represent a chair flip on a piece of paper, on the board, right, when we draw it out, we have to do a little bit of, of massaging of that chair, right? You can see I kind of did it up here with, as I've drawn the numbers. Okay, so carbon 1 is the carbon with the substituent, right? And then the chair on the left, you can see carbon 1 is in the top right corner. Okay, after I did the chair flip, carbon 1 is now in the bottom left corner. Okay, and that's because if I do a chair flip, you can see this carbon with the methyl group, right? The bonds going to that carbon are pointing up, right? These 2 black bonds are kind of pointing up, right? And so that's going to be the axial substituent, right? When I do the chair flip, which direction are those bonds pointing now? Now those bonds within the ring, those black bonds are pointing down, and the substituent is equatorial. Right? So here, right, the bonds going to carbon 1 are pointing up. In the chair flip, I can't have those same carbons still pointing up because that's not how a chair flip works. Right? So now those bonds to carbon 1 are pointed down. Right? Anytime you represent a chair flip in drawing on the board, on a piece of